Bismillah Rahman Rahim. In this video lecture series, I'll be covering concepts related to motion analysis and object tracking, a very important and vastly applicable domain of machine vision. Initially, I'll focus on techniques suitable for analyzing motion for extraction of motion behavior of the objects in question. Later, I'll move towards object tracking techniques being widely used in field of machine vision. In this first video, the discussion will particularly be on motion analysis, the background needed for it, and various assumptions and techniques that may be used. Later on, I'll discuss individual techniques in separate videos. The main motivating factor behind the advancement of motion analysis methods is the need for tracking a moving object, whether it is for surveillance, robot navigation, autonomous vehicles, or for any other real-life example. Huge amount of information is hidden in the motion behavior of a moving object. For example, by analyzing the motion of a predator, we can figure whether it is going to attack or not. In cricket, the biomechanical movement of a bowler running and delivering a ball can tell us about legalities associated with bowling, biomechanical impacts, and injury-prone movements of the bowler. Furthermore, analysis of motion patterns of fire spreading through the jungles can help us save many lives. These are few representative examples where motion analysis plays a fundamental role in defining our course of action. If we look around, we would figure out that how humans are utilizing motion analysis in their day-to-day tasks without knowing the formalities of it. Just to establish this point, think of a fighter jet flying around and how you can track its motion even if it is occluded by clouds for some time. I'll recommend you pause this video and think of at least one other example where you unknowingly use motion analysis. It won't be that difficult. For implementing something on artificial systems, which we as a human are doing, we first try to understand how we are doing it. Therefore, motion analysis must be understood in a way humans are doing it. Building on this knowledge, we can figure out that input for a motion analysis system would be a temporal image sequence, that is, images displaced in time. Additionally, a prior information can help us in making motion analysis easier. For example, in case of tracking fighter jet with our naked eyes, our brain somehow approximates the speed of the jet, and if it becomes occluded behind the clouds, then we use approximated speed and assumption that it won't make any abrupt direction changes to track the jet behind the clouds. Similarly, information of the environment, context of the scene, specification of the motion capture system are all part of prior knowledge that contribute towards helping us in choosing motion tracking and analysis technique. Before trying to recognize motion, we need to understand how and where we may encounter motion. So, in this context, there are three main groups of motion-related problems. The first one is the simplest, where we just need to detect any kind of motion. Normally, this kind of problem is encountered where security of any region or area is required. In such situation, any motion must be recorded and must not be ignored. These problems may work with static camera or cameras, as is the case of surveillance of your garage at night. The second type of problems that try to capture motion are the ones that not only require to detect moving object but its location as well at all times. Such problems may use a static camera or moving one. Applications focusing on detection of moving objects may only at first segment out the interested object through motion-based segmentation methods, and then later on may not only track its trajectory but may also predict its motion as well. Practical examples of motion detection and tracking are everywhere around us. For example, tracking of clouds and prediction of their motion. Other practical examples include motion analysis of autonomous vehicle, flow of air around the fighter jet in a wind tunnel, city traffic analysis, and many other can be seen by looking around. Applications in which camera is not stationary prove to be much more complex. The last category is the one in which 3D object properties are tried to extract from 2D images of a moving object taken at different time instants. Famous examples of this domain are 3D reconstruction of human faces using different 2D images, or similar concepts may be applied to generate 3D CAD model of objects by taking 2D images from various angles. Taking 2D images from various angles is achieved by moving the camera around the object, or nowadays multiple cameras are used to take all required 2D projections at the same time. It is quite well researched area where 2D images taken from various angles of an engineering part are used to construct its 3D model and hence generate codes for CNC machining and fabrication of a particular part automatically. Before diving into the techniques and ways to detect motion or moving object, we must be aware of the assumptions that are commonly used so that localization of moving objects may be simplified a bit. The first one is of maximum velocity. Remember the example of seeing a fighting jet flying in the sky? Our brain somehow assumes the maximum velocity of the jet, and if it becomes occluded, then we can very easily approximate where it might be. Similar assumption is followed while tracking moving objects in scenes. For example, if a scene is scanned at certain time intervals, then this interval multiplied with the maximum assumed speed will give us the distance that object might have traveled between successive scans. This can further be illustrated by supposing that in one scene a certain object is present somewhere over here. Then in the next scan, this object, if it will move with its maximum velocity, can be somewhere in this circle. The radius of this circle is nothing but the distance traveled by the object in the time interval, and it can be easily figured out using the time interval multiplied with the maximum velocity of the object. Another assumption is of acceleration. Commonly it is assumed that the moving object may have small acceleration between two successive scans. Recalling the example of fighter jet, if we approximate the position of the jet which is occluded and that position has some error in it, then it may be because of two things. Firstly, there might be an error in assumed velocity of the jet, and secondly, and more commonly, the jet might be accelerating or decelerating. Once again, suppose that in one scan a certain object is present somewhere over here and is moving in this direction. Then in the next step, we can approximate its location by using the assumed velocity, but considering that it may also have a small acceleration associated with its motion, its location might be somewhere in this region. A small acceleration will allow this object to be present over here or over here or over here or anywhere in this small region. Apart from assumptions related to velocity and acceleration, common motion assumption is also considered, which states that all points making up an object move in a similar fashion. So tracking a single feature point can be replicated to track other feature points in the object. Furthermore, the assumption of mutual correspondence allows us to track complete rigid bodies by tracking points on them and utilizing the fact that other parts will exhibit stable pattern of movement. Therefore, each point in successive scans will correspond to one corresponding point only, unless there is some occlusion or object has rotated to another 2D projection, increasing or decreasing its visible area. Suppose, for example, this object moves, then all points present on this object are going to move in a similar fashion. So tracking only one point will give us the result and will give us the motion analysis of all other points as well. Motion analysis may be divided into two separate but interrelated objectives. These two objectives or stages are not something which we humans are not doing. For example, for tracking a Formula F1 car of our favorite racer, the first thing we do is to localize the car and make representation of that car in our minds using its features, that may be colors, decals, or any other logo visible on the car. Once we have this representation in our minds, we use a priori information related to the racing track, occlusions, and estimation of car speed and acceleration to keep a track of it. Therefore, the first thing we need is to localize the object and generate its representation, whereas the second thing we need is trajectory estimation using all available information at our disposal, which majorly include a priori information about the type of motion, assumptions, and motion models. It depends on the application that which stage or objective will demand more effort and how much contribution it will have towards the final goal of tracking the object. For example, tracking an aircraft on a radar would rely more on motion models because its motion is much more predictable, whereas tracking human faces in crowded scenes would rely on localization and representation of target faces in images. Motion models will not suffice here because of the random and abrupt nature of motion. In this video, I tried to introduce various concepts and considerations associated with motion analysis through image processing. I'll explain few methods of motion tracking in subsequent videos that may be found in the links.